Hello people. If you don't really understand the fundamentals of how an Elasticsearch cluster works, what shards are, what they're for, or why they're so important, this video will help. It's part of a free short course I published to explain the fundamentals of Elasticsearch architecture, specifically shards. In this part, I work through how and why we could have theoretically built some of Elasticsearch ourselves. I found that this approach helps people grasp what shards really are, how they factor into a cluster, and why they're so important. I've worked with lots of people who don't have any real understanding of what a shard is, how many primary shards to use for an index, or how they affect cluster performance. I've made the course to have somewhere to refer people to so that they can fill that knowledge gap. The course also covers 3 very important shard-related questions to answer when managing a cluster, and I run some experiments to show how the number of primary shards affects the indexing rate and other metrics. I've put a link to the course in the description and look forward to seeing you there. In the meantime, enjoy this video, have fun, and cheerio. Let's say we have an application that runs surveys. It collects survey responses and comments from users and stores the data in a traditional relational database like Postgres. We're able to store and read the data really quickly and efficiently, but we now want to allow our customers to perform complex analytical queries and advanced full-text search. Postgres doesn't provide all the functionality we want, but there are other types of data stores specifically designed for what we want. We decided to copy the data into Apache Lucene, a mature, popular, well-maintained document store and full-text search engine. We write a bit of code to copy and continually synchronize the data from Postgres to Lucene, changing the data model into one that fits the type of queries that we'll be using. We then build a new analysis module for our application, which queries Lucene instead of Postgres, and develop some complex nested aggregations and advanced full-text queries. Our customers are thrilled with the new capabilities. They found new ways to use their data, enabling them to discover new insights to help their customers. The new functionality, coupled with outstanding feedback from our customers, attracts more customers to our application. More customers turns out to be a double-edged sword, because the extra load causes the analysis module to slow down and start giving errors. Let's figure out what's going on. When Lucene indexes a document, it doesn't just write that document to disk. It maintains what's called an inverted index, which is a data structure that tracks which documents contain certain values. When you query for documents containing the word yogurt, instead of reading in every document and filtering to just the ones matching a query, Lucene has a map to all the documents that contain the word in the form of the inverted index. Lucene can then tell you very quickly how many documents match and even which specific documents. You can think of it like looking for a certain Lego brick. Finding a certain brick in a mountain of Lego is possible but will take some time. If you sort that mountain into smaller mountains of grouped pieces, say by color, you'll find the pieces quicker. Sorting into more specific mountains, individual brick types, will make finding one quicker still. Categorization like this really helps with searching, but will make adding a new brick to your collection a bit slower, as you first have to find the right pile to put it in. Lucene maintains data structures like this not only for text fields, but also for all the field types it supports. The documents we're indexing contain hundreds of fields, and there's only a single Lucene process to do the work. There will be a limit to the rate at which a single process can maintain the inverted index and write those documents to disk before it becomes overwhelmed and begins queuing responses or throwing errors. This limit isn't a hard limit defined in Lucene configuration. It also can't be determined by a formula or spreadsheet. It's a threshold that can only be semi-reliably found by running experiments. Unfortunately for us, however, we found it in production because our system has been so successful. Everything was peachy until the indexing rate increased to, say, X documents per second. Now we have an idea of the threshold. How can we scale? We can't tell our customers to stop adding data or run fewer queries. We want more customers, not less. We found the maximum rate at which we can index documents with a single Lucene process and know there's nothing we can do to increase it that's scalable long term. Instead of scaling vertically by improving the host's hardware, we can scale horizontally. To be able to store 2x documents per second while balancing the search load, we run 2 instances of Lucene on the server and redistribute the data across both. We end up with one logical document store, with each of the 2 physical stores holding half the total dataset. With the data now spread over 2 stores, if a user searches for the word yogurt, we need to search both of these stores and merge the results. This is okay, but when the growth continues, we need to make sure that it's easy to scale further. Adding more Lucene instances to allow rates of 3x, 4x, or even 10x, and making sure they're searched needs to be effortless and possible without downtime. We can encapsulate all the Lucene-related functionality into a new standalone service that will deal with searching any number of Lucene instances for us. Instead of querying Lucene for documents containing the word yogurt, we'll query our new service. It will then forward the request to all known stores in parallel, fetch the results and combine them, then send them back to the client. It will also know which instance to store a new document in by balancing the number of documents across them so that each instance is searching roughly the same number of documents. This new service that manages the many instances of Lucene, coordinating search and index operations, that's the beginnings of Elasticsearch. The process started when you run Elasticsearch is called a node. The instances of Lucene being managed by a node are shards. A node is the new search interface, wrapping and extending Lucene's functionality. Shards are the scaling unit of our data. Customers continue to load data, Elasticsearch adds more shards to scale appropriately, and performance remains great for a while. Before long, there are 2 new problems. One is that the physical machine hosting Elasticsearch is running out of resources because of all the shards on it. Every shard, being an instance of Lucene in its own right, consumes system resources. There is only so much work that a single machine can perform, and the server will eventually run out of memory, CPU cores, and I/O bandwidth. The other problem is that when the server running Elasticsearch goes offline, we can't store new data or run searches. The application is out of action until the server comes back up. In larger systems, services and entire servers are guaranteed to crash, and we need to allow this to happen without affecting the application. Such a feature is called fault tolerance. Both of these issues, the server becoming overwhelmed and the system being unavailable when the server crashes, can be solved by distributing the shards over multiple servers. Each server has its own CPU cores, memory, and disks, relieving the current bottleneck. Plus, if one server goes down, there is still data to search and somewhere to store new data. Running Elasticsearch on multiple hosts is fine, but at the moment, these nodes won't know about each other. We need a way for the nodes to communicate so that they can automatically discover each other on the network and forward search requests. A user can then run a search against any of the nodes, and the node will relay the request over the network to the other nodes. This new inter-node communication channel is called the transport layer. Now, instead of a node running a search only on local shards, it also discovers and communicates with other nodes to search their shards. These nodes, working together, aware of and communicating with each other, form a cluster. There could be 1 node or 100 nodes in a cluster. Each node needs to keep track of which other nodes are in the cluster and which shards they host. That data, amongst some other cluster-related metadata, gets stored on each node in cluster state. The transport layer and the cluster state allow the dataset to be distributed across multiple servers, reducing the load on each individual machine. We now have a foundation to build a fault-tolerant cluster. Distributing the data helps a lot, but when one node goes down, it takes all the shards on that node with it. We can still search against the nodes that are up, but we'll only get partial results. To get complete results, we need to back up each shard on a node to a different node in the cluster. This backup shard, called a replica shard, will always be completely up to date with the original primary shard. Let's work through an example to see how this can work and figure out what else we need to build. Say we have shard P0 on node 0 and shard P1 on node 1. Now, network fairies break a cable and take node 1 offline. Because node 1 is unavailable, we can't search against P1, so any data stored on it won't be included in search results. If we were to have a replica of P1 that we could use when node 1 goes down, the replica would need to be stored on a different server, node 0 in this case. We enforce a rule that a replica shard can never live on the same node as its primary. Making this primary or replica state a simple label will mean that we can change a shard from a replica to a primary or vice versa almost instantly. We can upgrade cluster state to store not just which shards are on which nodes, but also whether those shards are primaries or replicas. To know when a node goes down, we can upgrade the transport layer so nodes constantly check in with each other. If a node fails to check in, cluster state is used to find the replicas of the now unavailable primary shards, and they are promoted to primaries. Going back to our cluster catastrophe, but with replica shards and the upgrade to the transport layer, as soon as node 1 goes down, P1's replica, R1 on node 0, will get promoted to a primary and become the new P1. Even though one node is down, all the data in the cluster is still available. And that's it. Data can be distributed across multiple servers and ensure fault tolerance by running multiple nodes and using replica shards. The application is now fast, scalable, and resilient. Our glory is short-lived, however. Scope creep. The functionality of Elasticsearch is now so good that the development team wants to use it to store and search their log files. Until now, all the shards have only been holding data about survey responses. The only reason we know this is because we've only been storing survey responses. So where and how do we add a completely different dataset? Remember that shards are our scaling unit. The log data would likely grow at a different rate to the survey data and is likely to be written much more than it's read, so could have different requirements for the number of primary and replica shards. With this in mind, it makes sense to create a new group of shards in our existing cluster just for the log data. We add a group label to each shard to indicate that a shard contains documents about survey responses or log entries. Elasticsearch will then know exactly which shards to query if we're only querying for survey responses or for log entries. We also hold details about individual fields that each document can contain, such as the field names and whether they're a string, an integer, an IP address, and so on. That metadata could be specified at the group level, since all shards in that group are holding the same type of data. This grouping concept, a group of shards where each shard is holding part of the same dataset, is an index. The field level metadata is called mappings. When storing a document, you interact with an Elasticsearch node at the index level. Have a survey response to store? Tell the survey response's index. The document will automatically be routed to a primary shard and also replica shards if needed. Searching for documents is also done at the index level. All shards in that index will be searched and any matching documents returned. We now have a distributed document store with fault tolerance and support for multiple datasets. That's Elasticsearch Architecture 101. We've covered an incredible amount here, but here are the main takeaways. Running Elasticsearch on a server starts a process, and we refer to this process as a node. A node stores data in multiple instances of Apache Lucene, each of which is called a shard. There are two types of shard. Primary shards are the main source of truth and are written to first when data is indexed. Replica shards are a mirror of a primary shard and are never stored on the same node as the primary and are written to only once new data has been successfully written to the primary. A dataset is stored in one or more shards which form an index. The number of shards in the index depends on many factors and there's no catch-all correct answer. The main purpose of the shard is to allow the index to scale. Nodes running on separate servers can be configured to create a cluster. Shards can be distributed across nodes in a cluster to provide fault tolerance. Every shard will occupy system resources, no matter how much work it's doing or how many documents it contains. Now, this section is a very high-level introduction to Elasticsearch's architecture. I've made a lot of sweeping generalizations and left out a lot of, frankly, very important detail. I've not mentioned things like node roles, how Vortex search works, aggregations, how data gets indexed, and so on. Later videos will elaborate on all of this and discuss much more functionality available in Elasticsearch and the Elastic Stack as a whole. Elasticsearch and the Elastic Stack are also much more than just a distributed document store. The extra features, however, like enterprise search, security, and observability, all store data in Elasticsearch shards, so knowing these fundamentals will serve you well.